All right, so RSA is going on this week, and you can get in for free on Thursday. And if you get an Expo pass, you can get in on other days, at least to the Expo. If you do any of that, it's worth extra credit. If you went to B-Sides or the Hack the Bay, that's worth extra credit. So let me know if you did those things. And I'm not going to do any of them because I don't want to be spreading my cold, although I did a remote session at Hack the Bay. Anyway, so here we are at 141, and we're nearly done with this class. In fact, today is the last lecture. There's only one more class, and I'm not going to do a lecture or present any new material. I'll just be there to help anybody that needs help. So we're going to cover TLS today, and I got a couple demos, and that'll be pretty much it for material in this class, unless something comes up from a question. So let's take a look at TLS in all its glory. All right, so we're going to talk about TLS, and the current version is 1.3, and we'll talk about all the improvements that went into 1.3. So TLS is at layer 4 of the OSI model. There's physical data link and network, which gets you through Ethernet addresses and IP addresses. Those get you to the actual physical location of the server you want to talk to. And layer 4 with a port number is how you communicate to the specific process at the other end you want to get to. And this can be protected at the transport layer by security. It adds encryption to the transport layer. Any kind of traffic can in principle move over TLS. The problem is, as versions went by, it got too big and bloated. It had many different protocols for encryption and handshaking and such, and it turned out a lot of them had vulnerabilities. And there was for the last 15 years, there's just been 2 or 3 major flaws every year. By the way, to be fair, a major flaw, like the Beast attack or the Crime attack, usually meant that if you could make like 100 million requests of the server, you could leak out some information about the key. These weren't, easy attacks, practical attacks, but you expect the cryptographic security to be really strong, where nobody can get in without the key. And these were flaws that meant that people could get in without the key, and typically they'd say if you had a fast connection, you could run this script for like 2 days, and at the end of 2 days you'd find the key. So that's unacceptable, and so they kept upgrading it to fix that. And PLS 1.3 was the latest big upgrade to really get rid of all these old dangerous algorithms and make it simpler, faster, and more secure, which shouldn't be surprising because I've said in practically every chapter of this class that there is a normal standard protocol, and then there is a new one that is in fact more secure and simpler and faster, and people just haven't bothered to upgrade because the old one's working. But in this case, the old one was not working, so people were motivated to move to the more modern, faster one. So what you want is a secure channel to make sure that data is confidential, which means that unauthorized parties will not be able to read it because they lack some secret key. Authenticated, you know who you're talking to. When you're logging into Google, you have proven that it's really Google and not someone posing as Google, and making sure you have integrity so the data is not modified on the way there. That's what you want. And that has to prevent adversary in the middle attacks, man in the middle attacks. So even if somebody is able to intercept your traffic and be in the middle, like your ISP is between you and the server, they won't be able to do anything. That's the idea. Because everything will be encrypted with a key they don't have. All right. Now, the reason this works, of course, is because we have these trusted certificate authorities, trusted third parties. So when you connect to Google, Google sends you a certificate, and you then consult one of the trusted third parties to say, is this really Google? And they say, oh, yes, in my database, I sold that certificate to Google, and that's the right identifying number, so I know that's really Google. So as long as you trust that third party, it's all trustworthy. Of course, you are trusting a third party. Nothing's ever perfect. So here's the requirements of TLS. It has to be efficient, so it doesn't burden the CPU too much. It has to work on any hardware or OS, has to be extensible, and it has to be versatile enough to carry all the types of traffic we want to send over it, which is a whole lot of traffic on the internet. So you get a protocol suite. TLS is technically not in the transport layer, it's above the transport layer, adding security to it. It can run over TCP or UDP. The UDP version is called DTLS, but you almost never hear about it. What we mainly hear about is the TLS protocol. So Netscape invented this. Before then, all the traffic on the internet was just not encrypted at all. And, nobody thought that was a problem because it was just a scientific experiment, and nobody was supposed to be doing shopping, and there wasn't any social network where you'd log into anything or anything like that, but they wanted to make it commercial and wanted to make it possible to do financial transactions on it, and you can't do that without encryption, so Netscape invented it. They invented SSL, Security Sockets Layer, and it turned out to have security flaws, and all of them are considered broken and shouldn't be used anymore. TLS started around the turn of the millennium, and 1.0 is the least secure. I don't know if anybody's using 1.0 anymore. 1.1 is probably the oldest version I've seen in use anymore, although there's probably some old server anywhere using any old version. TLS 1.2 is the main one, and 1.3 is the newest one, even better. All right, and notice this supported cipher block chaining, which we've exploited in the projects. That was considered hot back in the early 2000s, but it turned out that the padding oracle was a dangerous attack on it, and that caused people to lose their faith in cipher block chaining. So here you got a record protocol that encapsulates the data, and you have a handshake protocol that agrees on a key. So here's how it works. First, the client sends a SYN packet, TCP to the server, to see if the server is listening on the right port. The server says a SYN ACK, and the client sends an ACK, and now you've completed the TCP handshake, so you haven't set up any encryption yet, and you haven't verified that you know who you're talking to, but you have verified that you can at least communicate with that server. That server is in fact listening on the expected port so we can send data. So now it sends a client hello, which says, I would like to set up a TLS session. The server replies with a certificate in the server hello. So you get a certificate. Then, not shown here, the client verifies that certificate with a trusted third party, which is programmed into their browser. And if it passes that test, then they send this change ciphersec key exchange message to the server. Now, when the server sends this down here, we'll see these coming up in detail. I think it's the client hello that lists what available encryption techniques there are. We'll take a look. So that's the handshake, and you see it's a 7-way handshake essentially, well maybe 6. Anyway, it's a lot. So the client hello lists the available ciphers that the client has because the client is probably weaker and more limited than the server. So the client says, here's the encryption techniques I support. And the server chooses from among those, or it says, nope, I don't speak any of those. I cannot set up a TLS session with you, which is of course not common because everybody wants people to use their servers, so they make their server able to speak all common cipher keys. So here's the client hello from a browser with TLS 1.3, and you see there's a lot of suites here. AES 128, Galois counter mode using SHA-256, Cha-Cha 20, elliptic curve Diffie-Hellman exchange, RSA. All these different protocols are supported by my browser. So I tell the server, any of these 18 encryption regimes will work for me. And then the server replies, it picks one, hopefully the most secure one on the list. And then it says, okay, we're going to use this one here, which maybe I'm not going to see it here, but someplace in this mess it tells, here it shows TLS with Cha-Cha 20, and so on. So now that you've done that, in it comes, and it's going to send you a certificate to verify, and then you're going to exchange authenticated data. So the client generates a key pair, a temporary key pair, and the server generates a key pair. This is the handshake process. Then you derive keys with a key derivation function from the secret. This is Diffie-Hellman, essentially. And then you verify the certificate, verify the signature, and derive keys. That's the game here. So, all right. So the certificate authority, like I say, you have to trust these public certificate authorities. If they were to be compromised or to lie to you, then the trust would be broken. If they were compromised, and I was able to put up a fake website and get the certificate authority to believe that's Google, then I trick people to go to my fake website and it will tell them, oh yes, that's Google. Go ahead and tell that guy your Google password. That would be bad. That has happened a few times. And when it does, there has been serious investigation, and several certificate authorities have been placed out of business by letting themselves get hacked and not showing appropriate security. And all you have to do when they really, really mess up, then the browser manufacturers remove them from the trusted store, and now nobody uses them anymore. That puts them out of business in a hurry. So they have a strong financial incentive to protect their systems. Their certificate just looks like this. It's issued to a company. This is for Cloudflare.com. It had tell you what company issued it, and it has some fingerprints to identify it, and it has more information in here, including a public key. It has the certificate chain of trust. The certificate is Cloudflare, but was signed by this intermediate server, and that was signed by this root server, and that's the hierarchy. An early version of Microsoft's Internet Explorer actually failed to verify every step up here, so you could send a fake certificate and set up your own fake intermediate authority to vouch for it, and it would fool them. This is also a pretty common social engineering trick. I've heard of quite a few people that defeat social engineering capture the flag challenges by going somewhere and giving someone like a business card and say, oh, if you don't trust me, call my boss, and they dial that number, and that just goes to another one of their friends who lies and pretends to be their boss. So that's what this does. You ask somebody who's really not that trustworthy to vouch for them. The only thing that would really give it any weight is if you called somebody you know, who you trust, to say, is this really the right person? So the record protocol has the type of data being transmitted, a couple of bytes for historical reasons, fourth and fifth bytes are the length of the data transmitted, and the rest is the payload of data being transmitted. So it's pretty simple. TLS 1.3 also adds zero padding because of one of those attacks. I think it was the Beast attack. If it turns out the encrypted version of a packet is pretty much the same length as the decrypted version, so they were able to just look at the length of the packets, and they could deduce what website you were going to. I can just go to a website and use something like Wireshark and record the pattern of lengths of the packets that load that website, and then I can just look at the pattern of lengths in the encrypted traffic and deduce it. So they're now TLS lets you pad every packet to the maximum length, so they're all the same length to prevent that. All right, so there's three kinds of algorithms used. You have authenticated encryption, we talked about before, where you have not only encryption, but you have also a shared secret, so you know who you're talking to. We have a key derivation function, of course, which is just some kind of hash function with perhaps a salt and many rounds that derives a key from a shared secret, and Diffie-Hellman, which agrees on a shared secret without ever directly sending it over the network. All right, so there's only three algorithms approved. AES Galois counter mode, which I've said many times, is now the preferred recommended version of AES to use. There's another one called CCM, which is similar but some considered less efficient than AES, and Cha-Cha-20, a stream cipher combined with a message authentication code. The secret key can be 128 or 256 bits. The older versions used to use 64-bit and 80-bit keys. Those are not allowed anymore. Obviously, both of those are too short to be safe. I think a 72-bit key has been broken by brute force, but not at 80. And so, these are too close to being broken by brute force. Anything less than 100 bits shouldn't be trusted, and most people won't trust anything below 128 bits. So your key derivation function just uses a hash function and runs it through a bunch of hash operations and then keeps the first 128 bits or 256 bits so you get your key. We've done that in all the projects. So in Diffie-Hellman, you can use elliptic curve with the NIST curves or a couple of non-approved curves, which I say most people seem to prefer 25519 because it's not approved by NIST and we don't trust NIST anymore. And you can also use traditional Diffie-Hellman with RSA prime numbers. And like I say, the 2048 to 8192 bits is allowed. 2048 is now considered not really secure enough. We should be moving up to 3072 or 4096 pretty soon. And within the next few years, we should all be abandoning all this and moving to post-quantum cryptography. And there is a project where you do set up an HTTPS server to use post-quantum cryptography. So it's out there. It's not in your textbook yet because it's too new, but we did a project a few weeks ago where you do get to set this up and use it and see how it goes, which is what we're all going to have to move to pretty soon. So TLS 1.3 removed a whole lot of weak algorithms, MD5 and SHA-1, both of which are no longer trusted because they have collisions, RC4, which is no longer trusted because it's not white in the sense that it does not have an equal chance of producing every byte based on the input byte, and therefore there are patterns in the output you can use to derive the plain text. Cipher block chaining has that problem with padding oracles. And MAC then encrypt algorithms are considered less secure. So a lot of old encryption routines that are no longer considered so good have been removed and replaced by stronger ones. They've removed the data compression, like I said. That was at the crime attack. Oh, if you were going to compress the packets, then again, that would reveal some information about the structure of the packet. For example, if it had a whole lot of zeros, it would compress a lot. If it was essentially random bytes, it wouldn't compress as much. You could deduce something about the data or the level of compression, so they removed that data compression. And so it now has downgrade protection, a single round-trip handshake, and session resumption, new features. The downgrade attack is pretty simple. If you can get in the middle, which is pretty easy to do, then when the user tries to use TLS 1.3, you can just change that because at this stage it's not encrypted yet, right? When you're beginning a session, you don't have any encryption because you don't have a key yet. So they can say, oh no, she wants TLS 1.1 instead. Then the server will say, okay, I'll send you TLS 1.1, and then they can offer this person TLS 1.1, so she ends up using an older, insecure protocol. That's a downgrade attack, and this works for a lot of protocols. So they now have protection. What you can do, there's 8 bytes in the server hello to denote the TLS version. And so what will happen is you can check and say, did I really get TLS 1.3 or not with a packet? And they're cryptographically signed, so the man in the middle can't change them. So now your browser can check and make sure you really got the version you should have gotten. So that's the protection from downgrades. I don't know why you couldn't do that in the past. But anyway, it's there. In TLS 1.2, we saw there's a whole bunch of handshakes, and in TLS 1.3 they combined it into one round trip just to save time, because typically the latency, network travel time, is the main time cost in networking. So making less round trips is a considerable boost to security. And there's a thing called session resumption, where you can resume a previous session that's been disconnected briefly and continue to use the same shared key to make it more efficient. All right. And so TLS security, it authenticates the server with a certificate and a certificate authority. Typically the clients are not authenticated, but they can authenticate with a username and password in a TLS record or a secure cookie or a client certificate, which is rarely used. Normally you do this. You send a username and password to log in, and then you maintain your session with a cookie, which is sent over TLS. Forward secrecy is one of the main reasons people moved out of TLS 1.1 because of Snowden's revelations, revealing that the NSA was spying on all of us, spying on the traffic, hacking into web servers, and finding our traffic to decrypt. So people had a desire to upgrade to something with forward secrecy, so every session would have a different encryption key. So even if the NSA managed to steal one, they wouldn't have the persistent keys. That's 1.3 has forward secrecy. And so even if an attacker can steal a client's RAM, they only get keys and secrets for the current session or anything old sessions that are stored in RAM. They can't predict any future sessions. By the way, this is something I've demonstrated at Hope and made a big deal out of, at least as of a few years ago. If you logged into a browser with a password, that password was just sitting in RAM for a long time, and you could just use a RAM scraper to steal it out of there. And this is how the Target breach of credit card numbers worked years ago. They stole the credit card numbers out of RAM on the payment terminals, and I was disgusted at that time because Microsoft solved this in 2005. Since 2005, Microsoft has had this class called a secure string class, which automatically is removed from RAM when you stop using it, and developers just haven't been using it. So I was annoyed. You really should clear things from RAM when you're done using them. Server supports both TLS 1.2 and 1.3. Yes, that's right. Yeah, most servers support probably 1.1, 1.2, and 1.3 for just that reason, in case somebody has an old version of a browser. Like they might have an old iPhone or an old iPad that's using a really old version of a browser and they haven't updated. And so you have to decide when you set up your server, do you want to sell your product to people using old machines? Like especially people in foreign countries are often using very old machines like Windows 95, Windows NT, things like that. And so the question is, do you have customers like that? Do you want to serve them? Or are you willing to cut off those customers in order to have more security? That's your decision. Most people would rather just continue serving their stuff to every customer. All right, So things that can go wrong, if the certificate authority gets compromised, if it gets attacked and then people can change the certificates or steal the private keys, then of course you're toasted. This happened to DigiNotar. They made fake certificates for Google services. So that's a serious problem. And I think these guys were put out of business. This happened to 5 or 6 certificates around that time, 5 or 6 certificate authorities. Then, of course, this was a secret that came out in 2010. It turned out that there was a product you could buy that just has a USB port where you feed in a trusted root certificate so you can man in the middle HTTPS. And it became out that TrustWave and the other certificate authorities, quite a few of them apparently, had been routinely selling root certificates to law enforcement for surveillance, which breaks the model, and they would lie about it and conceal this. TrustWave admitted they'd been selling it. And everyone freaked out and said we should quit trusting TrustWave. And they said, no, you're not listening. You should trust us because we've quit doing it. All the rest of them are still doing it, all those ones you trust. So this is a sort of scandal, but apparently this was sort of well known in the industry, an open secret, that law enforcement can get a root certificate and impersonate a real certificate authority, and that even large corporations can do that. Because if you have a large corporation and you have a campus with thousands of users, you really want to inspect all their traffic to see if they're sending company secrets off, to see if they're sending like racist jokes through the email that will get you in trouble, and to see if they're downloading viruses. You really want to open those HTTPS sessions and see what's in there. Now, the official way to do this is to put a custom trusted certificate in their browser and then have your intercepting device have that certificate. But then they couldn't bring in their iPhone from home and use it on the network or anything. So in practice, it's better to just get a root certificate and impersonate a real root to do it. But it sort of breaks the whole trust model of the internet. And apparently this has been happening all along and sort of concealed. So, all right. Agogo in Flight also did this. They issued fake SSL certificates if you connect to their airplane connection here, and then, of course, in 2008, it turned out that the main certificate authority, which I think was RSA at this time, was using MD5 to sign their certificates, even though it had been decades since people warned you that MD5 had collisions you could generate. So they were able to actually fake a certificate by making another certificate with the same MD5 signature. It took a lot of calculation to do it. They did a cluster of 200 PS3 game consoles, but they did it. So it's that was what finally put the end to people using MD5 to sign their signature. They upgraded to SHA-1, and hopefully they moved beyond SHA-1 now, but even if all they did was go to SHA-1, that makes it a whole lot better. And then, of course, if you compromise the client, if I just put malware on your client, then I can read everything, get your session keys, read decrypted data. I can install if I get administrator rights on your machine, I can install a rogue certificate into your browser. So you will now trust my man-in-the-middle device. So that's a thing to know. If your client gets infected, then of course all bets are off. Then there are bugs in implementation. Heartbleed was an amazing problem in 2014 where you could send, for some reason, they wanted you to be able to keep the session open by just having a sort of handshake, ping pong go on. But for some reason, instead of just sending a ping and getting a ping response back, you would send them a word and it would then repeat that word back to you. I don't know why anybody wrote it this way, but that's what they did. And then what they did was they had you send the length of the word in the request, but they didn't verify it on the server. So if I sent a short word but put a long length on it, it would then send me the word followed by a bunch of random data from RAM. And therefore, you could dump some large amount of data, like 16 kilobytes or 64 kilobytes, off the server with every request. And you just get random junk from the server memory. And rapidly, we discovered that under certain conditions, you can get the private key for encryption from the server. So this means all the HTTPS servers were vulnerable, all the ones running Linux and OpenSSL that had this problem. And they had been vulnerable for years, and none of this information is logged. So all the security professionals had to go to their boss and say, all of our supposedly secure communications might have been compromised for the past 2 years. I don't know if it happened. I have no way to prove it didn't happen. And that's not a good thing. Say, how about that raise, Anyway, so that was a bad thing. By the way, if you used commercial software like Windows or Apple, you wouldn't have had this problem. It turned out it was Linux software that had this flaw. It was a pretty serious flaw. Of course, that's all been patched if you updated your stuff, but it was a really serious flaw. So there's an online test for SSL certificates you can use to rate your certificate and see how strong it is. And there's Let's Encrypt has become really important. A free TLS certificates for everyone. This has turned out to be incredibly popular. Everyone used to pay like $200 or more a year to get a TLS certificate. Now almost everybody uses these free ones from Let's Encrypt. When it first came out, people wondered if their servers would go down or the service would go broke or something, but somehow they're staying up. And now they're even moving to making certificates have a really short lifetime. So you renew them very often, like every week or two. All right. Now, there are other ways to improve HTTP. Strict transport security is a way to prevent people from downgrade attacks. Like you could go to a website and they could try to downgrade you to an unencrypted website, like from HTTPS to HTTP. And so what you can do is you can put this policy on your server and it'll put a header in responses saying, I will only talk to people over HTTPS. I will not talk to anybody over HTTP. That will tell the browser. There was another thing that was recommended for a while, public key pinning, where in addition to telling you I'll only talk HTTPS, I'll actually say I will only accept this public key here. So the first time you see that public key, record it, and if you ever see a domain pretending to be me without that public key, that's a fake one. Now the problem is there are times when you change your public key because you move to a different serving provider or your public key gets compromised and they didn't have any good mechanism to update it. So this actually leads to sites becoming unavailable after they pin the public key and then the public key changes. That turned out to be a huge problem. So after recommending this and rolling it out, they deprecated it and said, wait a minute, this turned out to be a really bad idea. Don't do that. So the replacement is now this thing called Expect CT, which is another way to try to prevent your browser from accepting fake certificates. I don't know exactly how it works, but it's the modern replacement for public key pinning. The only place I see public key pinning commonly now is Android apps. A lot of Android apps do this. I notice it because it's irritating when I try to analyze the effect of Android apps. They do sometimes have some kind of separate authentication of the public certificate, so you have to actually find that and kill it in order to intercept the traffic. All right, so let's try a Kahoot. This is chapter 13. Let me make sure I'm not confused. It is chapter 13. And that's here. There we go. All right. Someone with no name at all. Didn't know you could do that. By the way, I filled in the grades with A's for anybody who already has an A. There's several students that have already done that, so you'll see it in Canvas. If you don't have an A yet, I left the grade blank because you still have time to earn more points. All right, well, we'll carry on just so people can see the review questions. There ain't any competition with only one player, but that's life. All right. All right, so what version of SSL should be used? Yeah, none of them. They were all broken years ago. No version of SSL is safe. All right, which message lists many possible ciphers? Yeah, the client hello. Good. Which feature mitigates traffic analysis? Yep, zero padding means every packet is the same size, so you cannot look at the pattern of packet sizes to deduce information about the traffic. What's the shortest secret key used in TLS 1.3? 128, just like we talk about. That's what we all ought to be using at a minimum. All right? And which of these is no longer recommended? Public key pinning is the one that's no longer recommended. Expect CT is the replacement that is considered to be good. Public key pinning is the one that just created more problems than it solved. All right, so no name. So I don't imagine you'll get any points unless you tell me who you are. All right, anyway. All right, let me stop this recording.